At dawn on Saturday, March 1, 2008, a three-story building began moving slowly down a street in downtown Des Moines, the capital of the American state of Iowa. Above that reddish mass, nearly 705 tons of solid brick, mortar, timber, flooring, and century-old windows remained fitted together exactly as they had been when the building was completed in 1903. Below, concealed between the historic structure and the pavement of High Street, a steel platform rested on wheel modules comprising 192 smaller wheels, each powered by its own motor and each capable of turning 90 degrees without forcing the rest of the building to change direction. The building had not been dismantled. Not a single brick had been removed. No wall had been numbered and catalogued for later reconstruction. All three stories of the Murillo Flats, a IE 7-unit residential building that had housed families, artists, retirees, and a painter, were moving forward as if the ground beneath them had disappeared. Roughly 3 blocks ahead, a new site waited to receive the structure on a new foundation. And although everything about that scene suggested that making the building move would be the most difficult stage, that was nowhere near the most dangerous part of the operation. At first glance, a masonry building appears to be a single object. Walls and floors fused together, brick and concrete locked in place, end of story. The image most people have in mind is of a structure rooted to the ground, incapable of leaving its site without collapsing into ruins. That impression is not false. It simply describes how the material normally behaves, not the limits of what it can do. A solid brick wall can withstand immense vertical pressures, hundreds of tons per square meter, as long as those forces travel straight down through the material. What masonry does not tolerate well is the opposite. Tension, when a force attempts to pull the wall apart. Bending, when something tries to curve it. Shear, when two adjacent sections tend to slide in opposite directions. Torsion, when the entire building attempts to rotate around an axis. A difference of only a few millimeters between one corner and another, what engineers call differential settlement, is enough to open cracks in a wall that has silently supported the weight of 3 floor slabs for more than a century. Moving an entire building, then, is not a problem of brute force. It is a problem of consistency. The Murillo Flats did not need to become lighter. It needed to travel 3 blocks without any part of it moving faster, slower, higher, or lower than any other. Before examining how this was achieved, it is worth going back in time. The Murillo Flats was built in 1903 at 531 and 533 14th Street on the corner of High Street, within what is now downtown Des Moines. It was a small classical revival residential building containing 7 apartments across 3 stories, with load-bearing solid clay brick walls, sawn timber beams, ornamental facade moldings, and a restrained cornice along the roofline. Nothing exceptional, nothing monumental. Just one of those structures that, as the decades pass, goes from new home to old building to involuntary witness of a changing city. In the 1920s, Sisters Florence and Helen Wise purchased the building, and it remained in their family until the 1990s. It later passed through the hands of other owners, including an investor named Gary Bowen, who spent several years unsuccessfully attempting to convert the apartments into individually owned condominiums. On September 15, 2007, the health insurance company Wellmark Blue Cross and Blue Shield announced the purchase of 3 contiguous blocks in downtown Des Moines, approximately 6 acres of land, where it planned to construct its new corporate headquarters. Several historic buildings stood within those blocks, including the Murillo Flats. Demolition was planned, and this is where the first surprising fact of the story appears. The building could be preserved, but only if someone agreed to remove it from the site, with its walls intact, within a set deadline, before construction of the new headquarters began. That was when a local contractor named Mike Kinter, who had previous experience with historic buildings, entered the story alongside the Sherman Hill Neighborhood Association, which sought to rescue threatened structures and relocate them within the nearby historic district. Kinter hired Jeremy Patterson Structural Movers, a company based in the small town of Washington, also in Iowa, that specialized in moving entire buildings along American roads and streets. Patterson had already completed more than 2,000 moves, but the Murillo Flats was different. At that time, it would be the heaviest building the company had ever moved. And for a city like Des Moines, it would be the largest structural relocation in its history. Demolition, which had seemed inevitable, now had an alternative. There was only one small detail. 705 tons of brick had to be persuaded to behave like a single rigid object while crossing part of a city. The first layer of the challenge lay in the material itself. An old load-bearing brick wall is a curious thing. Structurally, it behaves like an elongated column. Each ceramic brick transfers the weight it receives from the brick above to the one below, while the mortar between them acts like an adhesive that distributes the load continuously. As long as the compression remains vertical and uniform, the wall is virtually indestructible through the passage of time alone. But apply even a small lateral force, or support that same wall at irregular points, and it behaves very poorly. Cracks can open diagonally along the natural mortar joints. Bricks can loosen. In more severe cases, an entire section can separate from the rest as though it had been cut from within. The first problem facing Patterson's engineers, therefore, was not making the building move. It was ensuring that, while moving, every wall continued to experience only the kind of forces it had originally been designed to withstand. The second layer involved the building's form. An ordinary building transfers its load into a foundation buried in the ground. That foundation distributes the weight across a larger area, preventing the soil from settling unevenly. To move the Murillo Flats, the engineers had to create a temporary foundation, a new base that would replace the original throughout the journey, collecting the loads descending through the walls and distributing them across enough support points to prevent anything from sinking along the route. This new base was assembled from a grid of structural steel I-beams, each comparable in scale to bridge girders, installed beneath the building in two perpendicular directions. One set of larger parallel beams, known as primary beams, extended along the building's longitudinal axis. Another set crossed beneath them transversely, forming what engineers simply call a grid. Every beam had to make firm contact with the brick walls, with no gaps and no excessive pressure, transferring the weight in much the same way as the original foundation. Where contact was missing, hardwood shims were inserted until the fit was exact. Where an irregularity appeared, the beam was modified or supplemented. Preparation took 17 days. During that period, virtually all the structural work was completed before the building moved a single inch. One crucial part of that preparation involved literally cutting the building away from its foundation. Water-lubricated chainsaws were used to separate the masonry from its original base, creating a clean line between the building and the ground below. The decision to use water as a lubricant had an elegant practical reason. Sawing through brick and mortar generates frictional heat. That heat can cause materials near the cut to expand, create microcracks, and compromise the wall's integrity. Water keeps the blade cool, clears cutting dust, and prevents particles from flying toward the workers. The cut had to continue around the building's entire perimeter, passing beneath every wall, every corner, and every internal pier. By the end of the process, the Murillo Flats was technically resting on its original foundations without any mechanical connection to them. It was an entire building sitting on a base that was no longer part of it. The third layer of the operation involved physics that was invisible, quiet, and precise. After the cut was completed, dozens of hydraulic jacks were positioned between the old foundation and the steel grid. Each jack functions as a small, pressurized oil pump capable of lifting enormous loads a few millimeters at a time. A single heavy-duty construction jack can support between 100 and 300 tons. Distributed beneath the grid, dozens of them shared the load. An operator cannot raise one jack at a time, because doing so would unbalance the building. All of them must rise simultaneously, at the same rate and speed, with the hydraulic pressure controlled through an interconnected circuit. That was how the Murillo flats left the ground, not in a sudden leap, but through a sequence of millimeter-scale movements, imperceptible to the naked eye, over hours of careful pumping. With every inch the building rose, hardwood cribbing was inserted beneath the grid, creating a stack that would prevent the structure from falling if a jack failed. The masonry was raised high enough for the transport modules, known as dollies, to be positioned underneath. The wheel modules are the most frequently photographed elements of these operations, but they are rarely the best explained. Each dolly is a small steel platform with independent axles and several pairs of solid rubber wheels. The Murillo's wheels were individually powered, and each could turn 90 degrees relative to the building's axis. Together, they placed a total of 192 wheels in contact with the pavement. That number was not chosen for appearances. 705 tons divided among 192 wheels equals approximately 3.5 tons per wheel. That figure remained within the load the asphalt and concrete streets of Des Moines could withstand without sinking or suffering localized failure. If the same 705 tons had been placed on 4 wheels, each would have needed to support 176 tons. No ordinary urban roadway can withstand pressure like that. The building would sink in the middle of the journey, break a buried utility line, sever the neighborhood's fiber optic cables, or worse. Multiplying the number of wheels was like multiplying the number of feet supporting the building. Each wheel could also be controlled individually, allowing the transport operator to negotiate complex turns, move diagonally, or rotate the structure almost around its own axis without transmitting torsion into the building. The city also had to be prepared. Before the move, engineers mapped the planned route along High Street, marking every location containing underground water, sewer, and gas lines. Municipal authorities were particularly concerned about the sewer system beneath the street, so the operation was scheduled for a Saturday, when traffic would be minimal and any failure would have fewer immediate consequences. Streetlights, overhead electrical cables, and telephone lines were temporarily disconnected. Where cables hung too low for the building to pass beneath them, specialized crews removed them and reinstalled them afterward. Tree branches were trimmed. Traffic signals were removed from intersections along the route. Before the building moved 3 feet, the street had already been transformed into a clear corridor, free of overhead obstacles, with the pavement inspected in advance to confirm its load-bearing capacity. Moving a building is not merely moving a house. It means temporarily reconfiguring a small section of a city. Then came the dawn of Saturday, March 1st, 2008. The first days of that week had been cold, with accumulated snow and temperatures close to 32 degrees Fahrenheit. But the weekend brought the kind of sudden weather reversal typical of the American Midwest. Temperatures rose above 50 degrees. The snow began to melt. The ground around the building, which engineers had expected to remain firm and compacted, turned into thick mud within hours. Moving the Murillo flats off its original lot and into alignment with High Street had been planned to take approximately 1 hour. It took more than 4. The wheels sank into the mud several times. The weight, precisely distributed across the platform, encountered ground that refused to cooperate for the first time. 2 heavy tow trucks from Hannafin Towing, a local company, had to be called in to supplement the pulling force of the powered modules. Meanwhile, the deadline imposed by the new owner of the original property was approaching, and concern that the entire operation might fail continued to grow among the engineers. Every additional minute in the mud meant 1 less minute available to cross the 3 blocks before the end of the day. When the building finally reached the asphalt and its wheels found solid support, the worst was over. But the day was only beginning. The journey across the 3 blocks was slow by design, not because of difficulty. A building carried on hydraulically controlled wheels travels at an almost absurd speed of only a few yards per hour. That slowness is not a technological limitation. It is deliberate. The lower the speed, the lower the acceleration. The lower the acceleration, the smaller the inertial forces acting on the walls. A masonry wall at rest is a safe wall. A wall moving smoothly at a constant speed is also safe. A wall subjected to jolts, sudden braking, or abrupt movement is a wall at risk. The Murillo Flats wheel modules moved in coordination through a central hydraulic system. If one section of pavement contained a slight change in elevation, the operator adjusted the height of the local pistons to compensate. If a turn was required, all the wheels rotated simultaneously into the same orientation. It was like guiding a heavy object across ice, while attempting to keep every part of it on exactly the same horizontal plane at every moment. By late afternoon, the Murillo Flats had traveled the 3 blocks to the site, prepared to receive it at 611 16th Street, in the Sherman Hill Historic District. There, a new foundation was already waiting, with dimensions calculated to match the layout of the building's load-bearing walls. Lowering the building onto its new base followed the reverse logic of the lifting process. The hydraulic jacks were gradually activated, reducing pressure at a controlled rate so that the weight of the 705 tons transferred slowly from the steel grid and wheels to the concrete foundation. New shims were inserted until the structure rested completely on its new support. The steel beams were then removed from beneath the building one by one, and the walls were finally reintegrated through a new structural connection between the building and its base. Throughout the process, technicians monitored every corner of the structure with laser levels, measuring any difference in elevation from one point to another. Differences of only a few millimeters were corrected in real time. The Murillo had crossed a city without losing its alignment. Not every building can be moved this way. Structures with pre-existing cracks, earthen walls, extremely tall buildings, structures with deep basements, buildings on sites with difficult access, or routes containing insurmountable obstacles are frequently excluded from consideration. The cost is also high. The Murillo Flats operation is estimated to have cost more than constructing a new residential building of the same size. But economic calculations are rarely the only consideration. Preserving an old building also means preserving the solid ceramic bricks that are now rare and expensive, its handcrafted interior woodwork, its ornamental facade details, and the urban memory of the neighborhood. In 2009, the building was added to the National Register of Historic Places, something that would hardly have happened if it had been reduced to rubble 1 year earlier. The operation was documented by television crews from the Discovery Channel and National Geographic Channel, and it became a reference for later operations, including discussions about moving a Czech and Slovak immigrant museum in the nearby city of Cedar Rapids several years later. Now, return to the opening image. The Murillo Flats, moving along High Street at dawn on a Saturday, with hundreds of tons of historic brick above and 192 wheels below. The wheels are still there, turning slowly, each under individual control. But they no longer appear to be the secret behind the operation. The secret lay in what remained hidden during the 17 days preceding the move. It lay in the steel grid that replaced the original foundation. It lay in the hydraulic jacks that raised the building millimeter by millimeter without allowing any corner to move ahead of another. It lay in calculating how many wheels were needed so that the divided weight would neither sink into the asphalt nor rupture a buried utility line. Above all, it lay in understanding that a masonry wall can support its own weight only while every point within it remains in a consistent position relative to all the others. What moved that morning was not merely a building. It was an entire system of precautions designed to ensure that nothing inside that building moved. Every ton had to remain motionless relative to every other ton, while the complete structure crossed 3 city blocks that, for several hours, had been reorganized to allow it to pass. To save a building, engineers had to teach it how to leave the ground. Keep following the channel for more stories in which engineering defied our intuition about the structures surrounding us.